Hi, welcome to my Lab 5, the Create Your Own Adventure Lab, and I chose to do one of the recommended ones, the rope swing. The purpose of this lab was to simulate the world's largest rope swing, and here's the video link, and I will show you a brief clip of the video because I think it was really cool. Wow, doesn't that seem like fun? And so we try to simulate this model in order to obtain some observations on how spring stiffness is so important in creating a rope that is used for a free-falling swing. We would expect that the greatest tension would be when the person is hanging directly at the bottom, as shown in this picture here. However, the greatest tensions happen anywhere but at the bottom, and later we will know why this is the case. The models and the principles used. The momentum principle, Newton's second law, and the spring stiffness were used to calculate the position, F-net, and modeling the tension force of the rope. It will become clearer once we look at the code. As you can see, the initial positions and everything is obtained through the behind of the scene video of the rope swing. Gravity, 9.8 meters per second. And the ball is a representation for a human being. And so the mass of an average male is 80.7 kilograms. We use the length of the rope, which was given in the video, which is 130 meters. The spring constant, I actually had to look this up online. And what I typed in was the average spring constant of a rope used in a free-falling swing. And it came up to be 10,000. Continue down. When you look here, you can see the momentum principle being used. And then you can see that I updated my position at every point in time interval. I calculated the respective components of the force. Net force. Right here. And then F-net, is the addition of F-net parallel and F-net perpendicular. And I need to calculate the force of the tension, which I need theta for. Come down, and the graphs is basically all the corresponding arrows that you will later see, and I made my code print out the final results of each corresponding components like tension, position, velocity, parallel, and perpendicular. Let's run the code. The red is the momentum, and the blue was the F-net, and the white was the force of gravity. At different time steps. So within the video, I set my time to be 13.7, which was how long it would take to make a half circle, which corresponds to a rope swing. And so I divided it into 4 different time steps. One was 3.425 seconds, 6.85 seconds, and 10.275, and 13.7 seconds. And by doing that, you can look at the final tension, and you can tell that the 6.85 is respectively lower than all the other tensions, which was around 1,000. And this makes sense because 6.85 is when the person is directly below the center of attachment, and there is not acting against gravity. When at other points of the circle, which was, at other points of the circle that was not here, it was acting against gravity, which corresponds why the tension of the rope was so high. Okay. So my success and failure at prediction. I believe my model was successful recreating the rope swing because by using the initial data that was given, it is shown that the rope did not intersect with the floor, meaning that in the real world, the person will not hit the ground. So that was really good. Although it could include errors like neglecting to include air resistance, which we know was really significant because of air drag when they were going up. Swinging back up. Okay? So what is optimum? It is important to know that choosing a rope that has a high stiffness lessens the chances that the rope will break due to a lesser amount of elasticity or stretch. Let's see this into play. So right here, remember I set my spring constant as 10,000. But I also looked up the spring constant of an average bungee rope, which happens to be 100. So when I run this code, you can see that it intersects with the floor, which means that basically the person actually hit the floor. So now you know how important spring constant is in determining to find a rope that best works when you're trying to free fall by swinging. It's not the same as a bungee rope. So this is my lab, and thank you.